Infinity is one of those words that feels harmless until you really let it into your physics. In everyday life, it's just a direction you can keep walking, keep counting, keep dividing, keep zooming. But physics is not a kitchen. It's the discipline of asking what happens when you calculate with an idea. With infinity, it stops being poetic and becomes predatory. It's a statement that the calculation has blown up. Your model has driven itself off the road. This leaves you with a choice that can keep you awake. Either the universe truly contains infinities, or your picture of the universe is wrong in some essential way. Start with the simplest place infinity sneaks in, the assumption of perfect continuity. The idea that space and time can be divided without limit. Cut a distance in half, then half again and again. You can do it forever on paper, so your mind concludes there are infinitely many points. Classical mathematics is built on that assumption, and it works unbelievably well. But it also produces nightmares the instant you try to attach it to physical things. Take the most innocent example imaginable, a point charge, a single electron. Its electric field, E tilde1 Ra, has energy density proportional to Ea, so near the point it goes like 1 Ry. When you integrate that energy density, the integral diverges at R equals 0. A point charge has infinite self-energy. Not very big, infinite. If you take the model literally, you can't even write down the total energy. In classical physics, you could try to rescue yourself by giving the charge a finite size, smear it out. But then you're forced to ask what determines that size, and you're no longer doing pure Maxwell theory. You're admitting the theory needed extra structure to avoid catastrophe. Now go to gravity. Newtonian gravity already has a one true force, and if you allow point masses, you can build similar divergences. But general relativity does something worse. It predicts singularities regions where curvature scalars blow up, where densities go to infinity, where the equations say, here, the concept of spacetime stops making sense. The center of a black hole. The Big Bang in the simplest cosmological solutions. These aren't just infinities in your notebook. They show up as predicted endpoints of realistic gravitational collapse. And when a theory predicts an infinity, it's either telling you that nature really reaches an infinite value, or it's telling you the theory has been asked to speak beyond its jurisdiction. Most working physicists treat singularities as signposts that general relativity is incomplete without quantum gravity. The theory that describes the universe on the largest scales breaks precisely where it claims something becomes infinite. Infinity is like a siren that sings, your map ends here. Now slide into quantum theory, where the problem becomes both more subtle and more humiliating, because quantum mechanics doesn't merely inherit classical infinities. It manufactures its own. In quantum field theory, the fundamental objects are fields, and fields have modes at all wavelengths. If space is continuous, then for every possible wavelength, there is a quantum oscillator mode. Even in the vacuum state, each mode has a minimum energy, the so-called zero-point energy. So when you add them all up, you get a sum over infinitely many modes. If you do it naively, you get an infinite vacuum energy density. Of dynamics, which predicts the electron's magnetic moment to absurd precision. But the existence of these infinities is not a minor technical nuisance. It's a structural fact about what happens when you combine quantum mechanics with the idea of a field that exists at every point in a perfectly continuous space. And this is where Feynman's relationship with infinity is interesting, because his entire working life was spent inside the machinery that produces infinities, and he was too honest to pretend he liked the way we handle them. In QED, when you calculate how an electron interacts with its own electromagnetic field, when you draw the loop diagrams, the electron emits and reabsorbs virtual photons. You discover that the integrals over all possible momenta blow up at high energies. The math gives infinity for the electron's mass and charge corrections. So what do? We perform renormalization. We say, fine, the bare mass and bare charge in the equations are not the measured ones. They are parameters we adjust so that when we combine the infinite corrections with the bare values, the observable result is finite. It works. It works unbelievably well. But if you're the kind of person who cares about what your equations mean, there's something deeply unsettling about a procedure that begins with infinities and ends with perfect agreement by redefining what you mean by the numbers in your theory. Feynman had a famously sharp way of describing this discomfort. He compared it to a kind of shell game, a trick where you hide the divergence inside the definition of a parameter, so the final prediction is finite. The dark part isn't that the predictions fail. The dark part is that the most successful framework we have seems to require, at an intermediate stage, that nature hands us infinities, and then asks us to perform an elaborate subtraction ritual to get back to reality. You can tell yourself this is just bookkeeping, and in a sense it is, but you can also feel, if you're not trying to fool yourself, that the bookkeeping is screaming a deeper message. Your theory is an effective description that cannot be trusted to arbitrarily small scales, because those loop integrals go to infinity precisely because you are summing over arbitrarily high momenta, arbitrarily short distances, assuming your equations remain valid forever as you zoom in without limit. Renormalization is not just a trick. It's a confession that zooming in forever is not a physically innocent operation. And this is where the concept of infinity stops being a mathematical curiosity and becomes a philosophical threat to the way people imagine understanding. In childhood, understanding feels like reaching the bottom. You ask why, you get an answer, and eventually you hit bedrock. But renormalization in effective field theory suggests a different picture. There may be no final bedrock accessible to us. There may be layers, each valid over a range of scales, each requiring new parameters and new degrees of freedom as you zoom in. And the infinities are the signals that you're trying to push a layer past where it belongs. The renormalization group the machinery that tells you how coupling constants run with scale turns this into a kind of cosmic warning label. The laws you write down at one scale are not the same laws you write down at another scale. You don't just learn, the charge is such and such. You learn the effective charge depends on how closely you probe it, because the vacuum polarizes virtual pairs screen and anti-screen, and the number you call the charge is scale dependent. So what is the real charge? Which value is the one true one? The answer is, the question is naive. The theory gives you a scale-dependent description. Demanding a single absolute number is like asking for a true coastline length. As you measure at smaller scales, you discover more structure, and the number changes. Infinity, in this context, isn't nature saying there's an infinite amount of charge. It suggests your demand for scale independence isn't compatible with how fields behave. Then we meet the cosmological constant problem. Infinity stops being a nuisance, becoming an existential embarrassment. Quantum field theory suggests that vacuum energy contributions so enormous, if they gravitated as general relativity predicts, spacetime curvature would be violently huge. Nothing like the observed gentle acceleration of our universe. We can renormalize many things, subtract reference levels. But the mismatch isn't a few orders of magnitude. It's an absurd gap. It makes us suspect we're missing a key principle about vacuum energy and gravity. We have theories spectacularly correct in particle physics and gravity, but combining them straightforwardly yields infinities or catastrophically wrong numbers. That's not a minor detail. It's a neon sign. It says, where infinity appears, our understanding is incomplete. You might think infinities aren't real, just artifacts. In many cases, that's right. A point particle, a sharp boundary, a continuous medium are idealizations. Infinities often arise when you take an idealization beyond its domain. But even with that comforting view, infinity still has teeth. It forces you to admit something human beings resist, limits to how finely reality can be carved. The universe may not allow the infinite resolution your mathematics permits. Maybe spacetime is quantized at the Planck scale. Maybe there's a smallest meaningful length. Maybe fields aren't fundamental, or how we sum over modes needs a different structure. We don't know. And that not knowing is the insomnia fuel. It suggests the universe might be built such that every time you push toward the exact, the infinitely small, the ultimate, the mathematics responds with infinity. An alarm that says, "Stop, your question is ill-posed." Infinity becomes the universe's way of refusing certain kinds of demands. And then you realize the truly dark possibility. Even if we find a theory of quantum gravity that removes infinities, you'll still question what you were doing when you asked for infinity in the first place. Because in physics, infinite often means you tried to treat a description as absolute when it was only effective. It means you tried to extend a model beyond where it earns trust. Your desire for a final continuous picture may be a psychological habit, not a property of the world. The nightmare isn't that infinity exists as a literal object. The nightmare is that your instinct for completeness may be incompatible with how nature is organized. We can build a ladder of theories: classical mechanics, quantum field theory, general relativity. Each rung might be astonishingly accurate within its range, yet none may be the last. Each time you push toward extremes, you hit singularities, divergences, or new phenomena. Infinity, then, is not a destination. It's a boundary marker that appears whenever you try to pretend there are no boundaries. Everywhere you've been quietly assuming the universe is smooth and complete, in the center of a black hole, in the beginning of time, in the self-energy of a point charge, in the vacuum energy of a field, in the sums that run to arbitrarily high frequency, in the integrals that ask, what happens at zero distance? So here is the Feynman-style conclusion, the one that is dark not because it's mystical, but because it's honest. Infinity is often not a feature of the world. It's a feature of our insistence on pushing a model past its rightful domain, and the fact that infinities appear so persistently suggests that going all the way down may not be a coherent physical demand. The universe may be such that each time you insist on infinite precision, it answers with a breakdown, forcing you to replace the question with a better one. That is unsettling, because it means the deepest layer might not be something you can picture, and it might not even be something you can reach by continuous refinement. It might require a conceptual jump as radical as the jump from Newton to Einstein, or from classical to quantum. Infinity keeps you awake because it's the shadow of a possibility. That reality is not infinitely divisible, not infinitely knowable, not infinitely smooth, and that the places where our equations blow up are not just technical messes, but messages from nature saying, you have reached the edge of what your current language can say.